Get your brains ready because this question is fun, twisty fun. MJ17 P42 Q9. A Hall probe is placed near to one end of a current carrying solenoid. Wow, what is solenoid? Go rewind back to our very first earlier videos, and that's when you see the different kinds of electromagnets that can generate electric field. But a solenoid, generally you can roughly know. Okay, let's say the current is flowing in the solenoid, current is flowing this way, goes through the solenoid and goes like zoop, 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 and finally goes back and into the battery. So if you use your right hand grip rule, your good sign, in the right hand, you know how the right hand looks like, you give a thumbs up emoji, like that. Yeah, so use your right hand grip rule on this thing and make sure you align all your fingers with the current, and your thumb will show you roughly where your magnetic field will be pointing towards. Okay, let's try that. So zoop. Okay, so we know magnetic field will be pointing kind of in this direction. Okay, of course, outside the solenoid is it might be a little bit more curved lah. So, sure, let's draw the whole thing. So it might look something like this, the magnetic field of this solenoid. Okay, just for you to know. Okay, so the solenoid has a current that generates the field. So the purpose of this current is to generate a B. Keep that in your mind, all right? Solenoid is generating current. Okay. And what is a Hall probe does? The Hall probe measures the B at a certain place. Okay. So important one to teach you how to write in paper 5 when you use a Hall probe as well. Okay, the probe is rotated about the axis and held in the position so that the Hall voltage is maximum. Why we do this? This is a very important step when you're trying to use the Hall probe in experiment. You must rotate until you reach a point, an angle. Rotate means like you take a ruler. Do I have a ruler? Take a ruler and then you rotate until, here is maximum voltage. Okay, then you fix the angle and use that as your measurement. Okay, explain why a Hall probe is made from a thin slice of material. Oh, this is about properties of a Hall probe. Thin slice. Why we use thin slice? Think back to your dimension when we draw the Hall probe. Something like this. The thickness matters, which is, let's say for example, this thickness. Because when you calculate Hall voltage, your equation is Bi over NTE. T is important if you want a Hall voltage that is as big as you can. So previously we see the Hall voltage actually is very small, which is bad. It's very hard to read, got a lot of fluctuations. So if you want to make a large Hall voltage, you got to make sure your thickness is very small because of this relationship. Hall voltage is 1 over T. So we must describe that. Explain why. Why you want that? Oh, because a thin slice, which is a small T, usually we say T gives a greater Hall voltage. And why? Must talk about the relationship. So you gotta mention that because here you can say the whole sentence. So Hall voltage is inversely proportional to T. And this whole sentence is based on this important relationship from the equation. Alright, so 2 marks here. Where do 2 marks come from? So if you talk about the goal of having a greater Hall voltage, so the purpose of thin slice is to have greater Hall voltage, that's 1 mark. And also you mentioned the relationship, Hall voltage inversely proportional thickness, that is the another mark, 2. Okay, so remember, explain why. Why thin slice? You want Hall voltage to be big because it's really small. Make it bigger, as big as you can. Reduce uncertainty in experiments. Part 2. In order for consistent measurements of a magnetic flux density to be made, the current must be constant. Explain why. Why must current be constant? Cannot have current changing one in this probe, for example. Can change current, change halfway one. Excuse me, you want to measure B, right? So we look at the equation once again. Hall voltage, Bi, NTE. You want to measure B, magnetic flux density. So you have to make sure everything is stable Cannot have too many changing things, okay? All this is constant already. So hopefully you want a consistent measurement. Your current should be constant lah. Okay, constant this. Then you can just use the relationship VH proportional to B. If you have a changing B, you change the B, you measure a different hall voltage. Very nice. Don't need to worry about current because current is constant. So that's why you gotta mention this obvious thing. Of course, you want to measure B with hall voltage. You have to keep your current constant. So you say the hall voltage depends on current as well. Not just depends on magnetic flux density, as you can see from the equation down there. So current must be constant if you want to use hall voltage to measure magnetic flux density. Can't have too many constants in your experiment. It's gonna be madness. 1 mark here, just be 1. You say lah, well, hall voltage depends on current, so current must be constant. Okay. So up till now, this question is still okay. Then you come to this next part. The probe is now rotated through an angle of 360 about the axis. Got rotation one ah. Ne? See the axis? And you see the arrow here? This one tells me that they're going to rotate they're going to do the queen wave like this. High hall voltage rotating. But they say at a certain angle 0, based on the graph, the hall voltage has a maximum value. Sketch the variation of angle with hall voltage. For one complete revolution. So you do a full turn of your Hall probe. Okay. So how do you draw this thing? I want you to, if you have not tried this, pause the video. Take like at least 5 minutes, 4 minutes, just try to brain the question and see, can you figure out how to do this? And then you come back and we'll look through this whole thing together. Okay? So go try it out. Try to see how to brain this rotating thing and what does the Hall voltage look like. Okay. So, in case you're not sure how to think of it, here's one tip. When things are turning and you find it hard to imagine, it's maybe good to use a different perspective. So now we're looking at the side view. This is what I call side view. But to see this thing rotating, it's best to use a top view. So something like this. Your eye is on top. You look down, you see a Hall probe rotating. And remember, there is a magnetic field going through this Hall probe like this. Okay, kind of maybe a little bit curved, maybe a little bit straight. But let's look at the animation to help us better understand how to draw the changes in V when you are rotating and why is there a change at all. Right, so I've replicated this whole thing here. How it will look like is usually, this diagram is obviously not to scale. You have a voltmeter or some kind of thing that can measure voltage, like a CRO, but I'm just going to draw a voltmeter for now for simplicity's sake. And you're going to connect the voltmeters, positive to positive, negative to negative, I suppose. So negative, negative, and there we go. Okay, so this voltmeter's purpose is to just measure the potential difference. Now, we need to create a scenario to help us think of it. Let's say I have set up this in such a way where I will feed a current in through the top. So let me add an orange color current. How about that? There we go. Or current come in, go down. So what you see on the right side here is the top view. You see this X? The X is where the current is flowing into the Hall probe. Okay, you compare the side view with top view. Then you see this little square here. That is this thing right here. So that's to orient, like which side are you looking at. So let's start off with the first thing they told us. They told us, number 1, that at theta is 0, the Hall voltage is the maximum. Let's say 10 mil lah. Maximum. Let's say I create values 10 mil. Okay. When will it be maximum? It will be maximum when the magnetic field is exactly cutting into the Hall probe like this. Got a nice 90-degree angle. Okay, so on the left diagram side view, you can say, going into the Hall probe. This one is going to be maximum hall voltage. So we're going to use this as our reference, 0 degree. Hang tight, okay? We're going to start rotating things. So if you find halfway like a bit confusion, just pause the review, rewind a bit. So this is 0 degrees. Okay, hall voltage maximum. Very good. Then what happened after that? Okay, let's rotate. So let's follow the rotation of a clock. So I'm going to take this and we're going to go rotate, rotate, rotate. Hall voltage will be changing. Let's stop right here. Okay, but before that, you know why got hall voltage, right? Oh yeah, I forgot to tell you. Okay, rewind a bit. So hall voltage here, let's assume that this thing is mainly to make our brains easier, p-type semiconductor. So all the positive charges coming down. Okay, so you have charges in the direction of this X on the right side here. So if you use your finger rule, you try to arrange and see where will the positive charges be going. Positive charges are, okay? So your positive charges, let's use red for positive now. Positive charges will all be gathering down on this side. All along, all the way down. Okay? So on the side diagram, you will see it like this. And of course, conversely, when you separate the charges, now the negative have to go somewhere, right? So your negative all will be on this side. In the side diagram, it will look something like this. Okay, so far so good. Now we rotate. Okay, let's go. Okay, so now we go zoom, rotate until, okay, let's stop here. Let's pause here a bit. Now what's happening here is now your magnetic field in your probe is at a different orientation. So I'm going to rub off the old setup because change liao. Now use your left hand rule and you have positive charges holes coming into from the top in. Stick your middle finger at the X on the right side. Where is the positive charges going? So you align, force pointing down. The force is always pointing down one. Yeah, the force is always pointing down. Might as well just draw like that. Okay lah, force pointing down. So force pointing down. So that means all the positive charges will go down. So they will start to collect here. Ding, 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 ding. And then by conduction, by separation, all the negative charges will be up here. Ding, 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 ding. Okay. So if you want to look at the side view diagram, cannot rotate that one lah, a bit hard. So I'll draw the magnetic field that is coming in on the red, going out on the black. Yeah, something like that. Okay. So look back on the right side, we have a problem here now. Your wire of the probe is connected to this red dot and this black dot. Got potential difference across here to here meh? All negative only wall. Hello? No wall. The potential difference here is between this plate. But your hall voltage that your probe is measuring is in this side. Oh no. This is what your meter is measuring. So your meter will measure nothing. No potential difference. All negative only. Where got potential difference? Face palm. Okay. So let's write down our part here. So when you have rotated to an angle of, let's call this 90 degrees, then your hall voltage is 0. Big fat 0. Great. Wonderful. Alright, let's continue our rotation. But let me label here first. Theta is 90 degrees. Okay, time for rotation. Let's go clockwise and we go zoom until here. Okay, so far at this point we have rotated a total of 180 degrees. So 0, 90, 180. So we are tracking where the black color is moving lah. That's why I write the angle in black. So now we are going to see what happens when you are at 180 degrees position. Where is the magnetic force pointing? Check. Middle finger into the X of the eye. The current is into the page. B is still pointing to the right. Force is still pointing down. But what's different is now where the charges will go. So now your positive charges, we are looking at the P-type semiconductor. Positive charges will now all come down here now. Zoom. And all the negative charges will now go up here. Oh, you see something interesting here. You are going to have a negative side. Why? Because in the beginning, we connect this red wire to the positive end of the voltmeter. Wo. But then why you got negative charge? So the voltmeter will read backwards and you have a negative voltage. Okay, time to write down. So you have a maximum value, but in the negative 10 mu volt maximum. Interesting. So you have maximum hall voltage here, but negative now, because you have swapped your terminals. Now the positive and negative is connecting on different side. If you don't know what I mean, rewind the video back to earlier and then you compare both pictures. Okay, take screenshots. Alright, so the last rotation, we're going to go to 270 degrees. So let's get rolling. I'm going to select my Hall probe and go rotate, 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 rotate. Check. Fleming's right hand rule. Point to the right. That's your pointing finger. Like this. Point. Middle finger, put at the current, point into the screen. Where's your thumb? Pointing down. Still down. Need to check, man, miss. Check lah, just in case, okay? You gotta convince our brains. Okay, where will the positive charges go now? Our positive charges, because it's a P-type semiconductor, the holes, will all be going down. So they will all gather here now. Oh no, this is the same problem like just now, leh. Then the negative charges will all be on the top part right here. Wrong color. sorry. Yeah, negative. So once again, you're going to have a trouble when you're at 270 degrees. Your Hall voltage is going to be 0. Why 0? Because you are measuring no potential difference. You are measuring between here and... Give me a black wire. Here. Got potential difference, meh? No. Potential difference is between here and here. This is the Hall voltage. But your meter is measuring between here and here. V meter. So your meter won't measure anything. It's just all positive. Wasted. So no Hall voltage here. Let's keep rolling and rotating. So just now was 270, right? Right here lah. 270. Where the black color is pointing. Okay, last one we go back to original now. So rotate, rotate, rotate. Wow, voltage will be getting bigger and bigger on the screen and you are back to original position. Yay! So back to original means you will have your maximum Hall voltage once again. So let's write that down. This is at 360 degrees. Hall voltage will be back to 10, which is your maximum. Why? Okay, double check. Left hand rule, point to the right. Middle finger into the current, the X there. Thumb will be down. Still downwards, miss. Why we check again? Okay, sorry. Now, positive charges all collect here. And negative charges go where? All collect on this side. So, it matches. Our voltmeter is happy. Positive charge, positive wire. Negative charge, negative wire. Okay, very good. So you will show a positive value. So this is how you can think of why is the voltage changing when you rotate. Okay, so now let's go back to the diagram and plot out all these points that we saw just now. So at the beginning, we have maximum. So let's put an X right there. Maximum Hall voltage. Because it tells at 0 degree Hall voltage. So okay, we call that maximum. Then we also have at the end 360. After one full cycle, you should be back to maximum Hall voltage already. What happens in between? When it is at 90, there is no Hall voltage because your meter is measuring across the wrong sides of the plate. So go rewind back to that video, take some screenshots and save it in your notes. And 270 also there is 0. No Hall voltage also because you measure at the wrong side. Then what happened at 180? You are reversed Hall voltage. So I need to find where is the negative Hall voltage. I think it is somewhere. Let me count the boxes. It's about 1.5 squares. Somewhere there. So this will be negative maximum. Because the charges are now reversed. They are on different plates. But your meter is still connected to the same side. Your meter got hole You poke a hole there already. See? You poke a hole there. You cannot just change the wire. Negative to negative. Okay. Then now the last one. 180. Okay, let's plot a point there. Okay, so we got a graph. What should we plot? A straight line? Should we do like this? That doesn't seem quite right though, because we are rotating angles. Why would there be sharp points like this? Doesn't make sense. It's kind of hard to draw that as well. So this sharp point here is a no-no. So the only other thing we can draw is a sinusoidal curve, a cosine curve to be exact in this case. So let's try. I will try to draw a sinusoidal curve. Okay, this is my best attempt now. So there we go. That's our sinusoidal curve to show how the voltage is changing between those two plates where you poke your meter in. You see the two holes? That's why you poke our meter ma. And where do three marks? Okay, where do the 3 marks come from? The first one is if you draw one full cycle of a sinusoidal wave. So that would be sinusoidal. One cycle, one complete cycle. Means you reach until 360 and your pattern repeat. Okay. Next mark is if you draw 0 and 360 is maximum. So at theta equals to 0 and 360, your V hall is maximum. So a highest possible value. Okay. The next one is going to be the negative. So down here, if at 180 degrees, your hall voltage is maximum but negative maximum, then you get the mark. The 90 and 270, they didn't really give a mark for it, but good to also plot lah, help you shape your curve a little bit to be more acceptable. So yeah, that's how you can think about how a hall voltage changes when you rotate. And remember, when you guys ever use a hall probe, whether in paper file or in real life, you gotta rotate your hall probe first. Rotate, because in real life the magnetic field is not so uniform and nice. And so you rotate it until you see, oh, at this angle is a maximum. So I'm going to keep my hall probe at that angle and then move it around to measure the field of whatever place. So you got to make sure the angle is the same. So that's kind of part of the setup and calibration of your hall probe. Okay, so that's all for this question. I hope that was helpful. You might need to watch this a few times to look through the animation again, but sure, go try it out. And make sure you understand what is happening when you rotate a hall probe. That's all for this video. I will see you in the next and final example.